Hello, I'm Piya. I'm an associate professor of electrical and computer engineering at UC San Diego. I primarily work in the field of signal processing and data science, and many of the research questions that I'm interested in can be unified under the theme of inverse problems. So broadly speaking, I'm interested in solving inverse problems, and there are two aspects of inverse problems that motivate my research. One is the sensing aspect, how to collect measurements in an efficient way that can help us solve these problems. And the other is the algorithmic aspect, where we try to understand how utilization of available information, some side information in the form of, the geometrical structure of the problem or some statistical priors that we may have access to, can work together to help us solve inverse problems in high dimensional settings. So before I zoom into the research, briefly, a little bit about myself. I did my bachelor's from IIT Kharagpur and my PhD from Caltech, where my advisor was Professor P.P. Before joining UC San Diego, I was an assistant professor of electrical and computer engineering at University of Maryland College Park. And during my PhD, I was also a research intern at Microsoft Research Redmond under the guidance of Dr. Henrik Malvar. My research has been recognized by a few awards. This is a partial list. The most recent ones are the 2020 IEEE Early Career Technical Achievement Award and the 2019 US Presidential Early Career Award, or the PCAS. Now, in a nutshell, if I were to describe what I do, I primarily work on mathematical and algorithmic aspects of signal processing and data science. And I am motivated, the main objective of my research is often to extract meaningful information about certain quantities of interest from measurements that are collected under challenging conditions, which means you may be collecting measurements which are contaminated with noise or contaminated with interference, which are specially designed, okay? Which may be even correlated with the data, with the signal of interest, let's say. Or you may have insufficient amount of data, sample star settings, or corrupted data, and so forth. So I like to ask questions like how something is done and why something is true, but I have a natural bias towards understanding why and why not, okay, beyond the hows. So my research, the main theme, the central theme of my research is, as I said earlier, efficient inference using a combination of sensing design of the sensing strategy, and also design of the algorithm that can work hand in hand with the sensing strategy. So this research can be actually broken down into some concrete subtopics. I've tried to do that in this slide. So the bottom two are collaborative research, interdisciplinary collaborative research that I do with my collaborators. And the top three are the core of my research, where kind of I work with solely with my own students. So in the core of my research, as you can see, the main theme is, again, solving these difficult inverse problems in high dimensional settings. And to facilitate solving such problems, you first need to understand what kind of sensing strategies are fundamentally better than some others, okay? So what kind of sensing strategies work better in what scenarios also depends on the physical model of the problem. So it is guided by physics of the problem. So you have to obey the physical constraints and design your sensing strategy such that you can use you can extract maximum amount of information that is possible from the measurements, okay? So this gives rise to the topic of computational sensing with sparse arrays, which I will elaborate in a moment. And this topic has also created a new paradigm in sensor array processing by showing that it is fundamentally possible to overcome certain barriers, which were long considered to be fundamental barriers, but they are not fundamental. They are fundamental as long as you stick to a certain kind of sampling strategy. If you go beyond that sampling strategy and play around with how you're going to design your sensing strategy, then those barriers can be broken. I will show you what I mean. And more recently, what happens is you see, to solve this kind of inverse problems, we need some low dimensional structure. Okay, we need to exploit some priors, some low dimensional structure that is present in the signal of interest. However, the traditional way or the classical way of doing this is to select handcrafted priors, which means priors which are pre-designed, such as sparsity or low rank or some low dimensional structure imparted by the manifold on which your signal resides. Okay, so these are all handcrafted priors. So driven by the recent success of machine learning over the last 10 years, there has been a push towards incorporating learned priors or learning the priors. Instead of saying, oh, I will use sparsity, let us try to understand what low dimensional structure is hidden in the signal of interest, okay, by learning a generative model for my object of interest, in this case, possibly images, let's say. So this has led to this topic of machine learning for inverse problems, which I have been working on recently. And many of my things that I developed earlier can offer very new insights onto this problem as well. So to illustrate a quintessential inverse problem, let's consider the problem of target localization by radars. So a radar collects samples along fast time, slow time, and angle, right? Fast time is for range, slow time is for Doppler, and the angle is to perform a spatial filtering of which directions the sources are coming from. However, your goal is to ultimately estimate 3 parameters per target, right? Distance, direction, and velocity. So although you're collecting a lot of measurements, you actually want these 3 numbers. So this leads to the question that, can we work with fewer measurements? If so, what is the fundamental lower bound, okay? How many measurements do you need to identify a certain number of parameters, okay? And if you know something else about the parameters, okay, then that can also be incorporated in deciding the fundamental bound. Now, once you know the fundamental bound, how to develop new sampling strategies that can possibly come close to this bound. The sample complexity can be achieved or not. And how to extract information from these kind of sampling strategies, from the measurements collected by these kind of sampling strategies. So I will show you that sparse sensing geometry actually provide a very promising answer to these questions. And it enables us to do something that we could not have done with uniform sampling strategies. So to illustrate the power of sparse samplers, I will again look at a very fundamental problem that arises in many applications, that is of source localization. So it arises in apparently diverse applications such as super resolution microscopy, to neural decoding of neural spiking activity, to radar target localization, and more recently in millimeter wave communication, where the channel is specular and has a sparse, and it exhibits sparse scattering, which makes the problem of channel sensing very similar to that of direction of arrival estimation. So, excuse me. So these are the applications of this problem. So let's try to understand what was the fundamental bottleneck using conventional sampling techniques, okay? So in sensor array processing, conventional sensor geometries are those of uniform geometries, where you place the sensors equidistant from each other, okay? So suppose in a line, you place them at the distance between any 2 consecutive sensors is the same. So the long-standing belief in array signal processing was this, that the number of identifiable sources, the number of sources that you can identify with a certain number of sensors, has to obey this bound. That number of sources has to be less than the number of sensors. And this bound is not, just a rule of thumb. It is actually fundamental. This bound is obeyed by uniform geometries, uniform linear array, uniform rectangular array, and so forth. So the question is, can we think of even identifying more sources and sensors? It is even possible. It's clearly not possible with uniform geometries. However, by changing the sensing strategy, in particular, in this case, by going beyond uniform geometries, you can actually identify more sources than the number of sensors. So specifically, I designed sparse arrays such as nested and co-prime arrays. They have a certain geometry, a special geometry. Using that geometry, you can develop algorithms that can exploit that geometry and the structure and identify order of m square sources with only m physical sensors. Moreover, they can also resolve two very closely spaced sources or closely located sources, which is beyond the resolution limit of uniform arrays. So both of these advantages are there. And these can be backed up by rigorous theoretical guarantees. Why does this happen? This happens because of a very interesting property of the sensing of how this sensor arrays actually perform source localization. So what happens is, what I have shown is that when you do source localization using sensor arrays, what matters is not where the sensors are located. Well, they matter, but they matter through something called the difference set. Okay, what is difference set? You look at all the possible sensor locations. Let's say they're located D1, D2, D3, whatever, and you take their pairwise differences. So D2 minus D3, D4 minus D5, D6 minus D3, and so on and so forth. So M choose 2 differences. And if you can imagine a new virtual array where you place sensors at the positions which are indexed by this difference set. Okay, so the difference set is actually what decides how many sources you can identify, number one, and number two, your fundamental resolution limit. Both are controlled by this difference set. So from this point of view of difference sets, uniform arrays are actually highly suboptimal, because uniform arrays, they're difference sets. If the uniform array has m elements, the difference set only has 2m minus 1 elements. Okay. Whereas if you change the sampling geometry in a certain way, in particular using nested or co-prime array, you can actually create difference sets which are much larger in size, which can actually have order of m square elements. Hence, by developing suitable algorithms, you can exploit this large difference set of these sparse arrays and identify more sources and sensors. So this is just an example of how this, how an image or a super resolved image looks like when you use a uniform rectangular array versus a nested array in 2 dimensions. Both have the same number of sensors, but the geometries are different. So just by changing the geometry and by developing suitable algorithm that can exploit that geometry, you can actually super resolve these sources, which is not possible using uniform rectangular array. Now, you see, central to the idea of sparse arrays is the theme of doing more with less. I can identify more sources with fewer sensors, right? So this philosophy actually translates very well to this problem of millimeter wave channel sensing. So in millimeter wave systems, what happens is they are deployed with a lot of antennas because of the small wavelength. You can pack a lot of antennas into a small form factor. However, you cannot place an RF chain at the output of every antenna because it is too power hungry. Okay, so what is typically done is the antenna, the information from all the antennas are combined through typical in analog beamforming circuit, and then at the output of the analog beamforming circuit, you only use a few RF chains. Okay, so this analog circuit acts as something like a dimension reduction operator. It is basically reduces the dimension from the antenna space to the beam space. Okay. Now this reduction in dimension can be facilitated in a much better way by using ideas from sparse arrays. So one way to reduce dimension is to just subsample, right? That's not going to work so efficiently. So nested array can be thought of as a new way to perform dimension reduction. Okay. And it works very well because the millimeter wave channel is specular in nature because of the sparse scattering environment. So it is a perfect application of this idea of nested array, but in a different way. You turn the idea around. Okay. So this is the main idea, that you can actually embed a sparse array into the reduced RF chain architecture, and you can reduce the number of RF chains significantly without performance loss. And this idea was a finalist for the Qualcomm Innovation Fellowship 2020. Where my student Pulak Sarangi teamed up with Rohan Pote, who is Professor Bhaskar Rao's student, and they were one of the finalists. So I will end my talk with a small, with a brief discussion on generative priors. So what are generative priors? So An inverse problem, broadly speaking, is something like this. You collect measurements, let's say Y, where the measurements are related to the object of interest, let's say a signal or an image, whatever, through an operator A. So you are observing X through this map A. And there is also possibly noise N added to it. Okay. Your goal is to invert this operator A, forward model, and get an estimate of X. And with noise, this problem becomes quite challenging. But even without noise, even if there is no noise, this problem can be quite challenging if this map is ill-posed. So best way to understand ill-posed map is it's many to one. So basically, many possible X's can map to the same Y. And then this map becomes non-invertible. So in such a non-invertible case, it is very difficult to guess what the true X was, right? It's impossible, unless you know something about the true ground truth. So this knowledge about the site information about the ground truth is expressed variously in the form of, additional structure that you have, or in terms of probabilistic priors, or these days, even in terms of generative models. So you assume that X is coming from a generative model, and the generative model is described using a neural network. So the structural prior on X gets mapped to the architecture of the neural network. And the architecture itself acts as a regularizer to your inverse problem. So this is the kind of problems that I'm looking into currently. And here a goal is to actually come up with, in many cases, you can actually have role in controlling this operator A. And this is the sensing design part of it, okay? Now, to give you a very sneak peek into one of our very recent results, this is with my collaborator Takaki Komiyama and his postdoc Ryoma Hattori and my graduate student Pulak Sarangi. So this work actually tries to solve a very difficult inverse problem, which is ill-posed. What is the problem? You're trying to decode neural spiking activity, which is occurring at a very high rate, let's say 1 kilohertz or even higher, from calcium signals, which are very slow, which do not have significant high frequency components, okay? So because the signals are very slow, the measurements are very slowly varying, so they are sampled at a low rate, let's say 60 hertz. So from signals which are sampled at 60 hertz, you're trying to infer a neural activity which is operating at a much higher rate, 1 kilohertz. Is there any hope? It's a very ill-posed problem. In this case, that operator A is definitely many to one, okay? So is there any hope in solving this problem? So we showed as yes. So people in neuroscience typically use sparsity, but even when they use sparsity, they only get a spike representation, which is at the same rate as the calcium. So if calcium is sampled at 60 hertz, they also get a spike estimate, which is at 60 hertz, okay? So we are trying to do something different. We're trying to get the spiking estimate at 1 kilohertz. Is there any hope? So what we did was we came up with a new generative model that captures this dynamics between slow calcium and, fast neural spiking activity. And we also use the fact that neural activity, in addition to being sparse, it has some other properties. In particular, it is binary in nature. Okay, it can take two possible values, non-zero value with a constant amplitude and zero. So using these two facts together, we were able to come up with a computationally efficient algorithm, actually, that can give you very highly accurate estimates of the underlying spike dynamics from this low rate calcium measurements. And we have conducted extensive experiments with benchmark data sets as well as experimental data sets, and it shows very good results. So we are very excited about this. And this is a quintessential example of solving inverse problems with priors. And in this case, the priors are in the form of binary nature of the spiking activity. So thank you for listening to my presentation. I will just close the talk with telling you about my students. So Pulak, Mehmet, Jiawen, and Sina are current members of my group. And my group alumni are Dr. Hang Chiao and Dr. Ali Kuchakzadeh. And these are some of the awards that my students have won, and I'm very proud of them. So if you have any questions or comments or feedback about any of the things that I talked about, or if you want to talk about any other topic that I could not cover today, please feel free to get in touch with me. I look forward to your questions and comments. Thank you.